Hello, this is David Harper of the Bionic Turtle with a brief tutorial on error types in statistics, and specifically type 1 versus type 2 error types. Now, this is at first glance a difficult idea, but I will say it turns out to be very profound in application. So this idea of the fact that we need to make error trade-offs in our error types when drawing inferences from samples, this comes up pretty much all of the time. So to illustrate, I'm going to use the normal distribution curve. Now this is a density function with mean of 0. It's also a standard normal distribution, and that means by standard I mean the mean is 0 and the standard deviation is 1. Now, in any number of scenarios, we may think we know something about some underlying population parameter. This could be the expected return on equities. This could be the difference in volatility between a hedge fund and a mutual fund. Any number of scenarios where we may think we know something about the underlying population parameter. The problem is, in practice, we rarely have the time or resources to actually go out and measure the entire population. If you think about, for example, the United States Census that is conducted every 10 years. They don't count all of the people in the country. That would take too long and be too expensive. They collect sample data and draw inferences about the population based on the sample. In fact, we could say that's really what statistics is about. The science of making an inference about a population based on a sample. So we may think we have a hypothesis about the population parameter. In this case, I'm going to keep it simple and assume we think the population parameter is 0. Now that is our null hypothesis. Our null hypothesis is that the population parameter is 0. Then we go out and we collect or analyze a sample, and we find that the sample statistic maybe is fully -2 standard deviations to the left of 0. So what we found is our sample statistic is different than our population parameter, or what we thought it was. And what are the possible explanations here? Well, really there are two. One is that we were wrong about our null hypothesis, that the population parameter in fact is not 0. The other possibility is that the population parameter is 0 and our sample is sufficiently small that it's possible, due to random variation, that the sample statistic comes out here. In fact, if you look at the normal curve, it implies an outcome, -2 standard deviations, is perfectly possible, perfectly plausible. So we really don't know if our population parameter is 0 or not. Our null hypothesis is that it is 0, but we get a sample statistic, and we'd like to be able to decide. We'd like help on the decision as to whether the population parameter is 0 or not. So now I'll add some numbers here, and again I'll just remind our null hypothesis is that the population parameter is equal to 0. And now if we think about a 95% confidence interval that is two-tailed, well, all that means is that if we go out here to the left about 1.96 standard deviations, and when I say two-tailed I mean we go out to the right as well, see how I've sliced this normal distribution, I've bounded it with an interval. All of the area under the curve constitutes 95% of the area under the total curve, and that means we have 5% outside this interval. That means we have 2.5 on this side and 2.5 on this side. So we can say if the normal curve fits our data, that's a real questionable assumption, that just by sheer randomness we expect 95% of the observations to fall within plus or minus 1.96 standard deviations. Now if we do a one-tailed test at 95%, then that means 5%. Now I've shifted to the green line. That means 5% of the area is to the left and 95% of the area is to the right, and our green line is going to be instead at 1.64 standard deviations. So that is still 95% confidence, but it's one-tailed because we're concerned about the 5% that falls to the left instead of the 5% that falls outside on both sides. Now we are in a position to understand the errors that can be made. if we find that a sample statistic lies out here to the left of this purple line, then maybe we want to suspect that our population parameter is not 0. It's so far out here to the left that maybe the population parameter isn't 0 and we're wrong about the null hypothesis. Well, 5% of the time, the normal distribution has told us that 5% of the time, just randomly, we are going to fall outside of this. So if we reject our null hypothesis, it's possible that in 5% of those cases, we are rejecting something just because it happened randomly. So now I'll shift this graph here down to the right, and I'll put this into a grid, which we sometimes see in finance texts, helping to explain this. But I'll remind you here on the graphic, if our null is that the population parameter is 0, and then we find a sample statistic that is non-zero, then we can make 2 decisions and we can make 2 errors. And so that's the point of the tutorial, that we can make these 2 errors. The decisions are, first consider a correct decision. We accept the null hypothesis, and in fact, in truth, the null is equal to 0. Well, then we've made a correct decision. We have correctly accepted the null. Now we can also choose to accept the alternative. We might say that is to reject the null, loosely speaking. That's almost true. So in that case, why would we reject the null? Well, that's because we found the sample statistic way out here to the left, and we decided that, due to randomness, that's just too far out. The null must be wrong. So we reject the null, or we fail to accept the null, in favor of accepting the alternative. Now, if the null is false, notice that can also be a correct decision. So, in short, we have 2 correct decisions. We can accept a true null, and we can reject a false null. Notice that also allows for 2 error types. First, we can accept the null, and in fact, the null was false. So our sample statistic could be out here to the left. We decided so far out to the left that we have to, or I'm sorry, let me say that again. It's out here to the left, but we decide that could be due to randomness, and so we accept the null. We say, well, the population parameter's probably still 0, and this is just due to randomness, so we accept the null, but the null turned out to be false. We've just committed a type 2 error. We predicted 0 for the population parameter, but in fact, the parameter was non-zero. And the other error type is, again, we're out here with the sample statistic, and we decide, no, randomness could not explain that. We must be wrong about the null. The null must not be 0. We're going to reject the null and accept the alternative. And what if it turns out the null was 0 and this was just randomness on the tail? We have just committed a type 1 error. We have predicted non-zero for the null, but actually it was 0. And so we can see this is a fundamental idea, and the reason I said it comes up so often in practice is it turns out if we're trying to infer something about a population from a sample, there is no way to overcome this. We can create decision frameworks that say, well, if I'm going to make an error, I'd like to bias in favor of a type 2 or a type 1, or I'd like to bias in favor of a type 1 instead of type 2. But we will find we'll always have to make trade-offs simply because we are uncertain about the actual population parameter, and a lot of what we really have to do is decide which error is more expensive to us. So that's an introduction to type 1 versus type 2. This is David Harper, the Bionic Turtle. Thank you for your time.